So I'm a PhD student from the French Alternative Energies and Atomic Energy Commission and at Les Mines de Paris, and I'm going to talk about the fracture toughness of Zircaloy 4 cladding in case of delayed hydride cracking. So we are studying Zircaloy 4 nuclear fuel rod cladding. So you can see here a picture of a fuel assembly, and here a zoom on a fuel rod cladding. So they are the first safety barrier of pressurized water reactor, and during their use in reactors, they absorb hydrogen due to corrosion by water. So after their use in the nuclear reactor, they are stored, and one solution is called dry storage. And you can see a picture here of cask storage in Switzerland, so you already have seen this picture. And the fuel rods are stored into a closed container to cool slowly, and they are subject to an internal pressure, and if it exists a sufficiently large defect in the material, it could lead to delayed hydride cracking, or DHC. So our objective is to provide a quantitative cracking model based on experimentation, allowing to evaluate cracking criteria as a function of thermomechanical history and irradiation. So to do that, we set up an experimental study in order to investigate the DHC crack propagation in the radial direction of fuel rod cladding, thanks to this specimen geometry called notched shearing. And we set up a numerical study to model DHC and to quantify the cracking criteria. And of course, those two parts are interacting. So now I'm going to talk about the delayed hydride cracking. So it can be divided into two steps. And the first step is the stress-induced diffusion of hydrogen in solid solution, so it's the wet pants, and at the notch tip, and the precipitation into hydrides once the solubility limit is reached. This solubility limit is called terminal solid solubility in precipitation, because as you can see on this figure, showing the hydrogen content in solid solution as a function of temperature, the terminal solubility, the limit of solubility, in dissolution here and in precipitation is different. So during our tests, we want to apply 250 degrees. So at room temperature, there is no hydrogen in solid solution. So to be the nearest by the terminal solubility in precipitation, we have to heat up to 350 degrees, then cool slowly to 250 degrees. So this is the first step of our experimental procedure. And the second step is a mechanical test, the second phase, it's a mechanical phase where we apply a load to our specimen, which is placed into two slotted springs in order to limit friction during the test. And this load is applied during a time t-test, and if nothing happens after 24 hours, the test is stopped. So I'm going to show you some results. So I will show you the load displacement curves for tests at 7, 11, and 30 Newton, and the microscope observation associated to those tests after a chemical attack to reveal hydrides. So here you can see results at 7 Newton, 11, and 30. So as you can see, there is no crack initiation for all of those tests, so they were stopped after 24 hours. And we can observe two things. So the first one is the increase of hydride concentration at the notch tip. So that highlights the stress-induced hydrogen diffusion at the notch tip and the precipitation into radial hydrides. And if you look at the length of the hydride at the notch tip, so it's shown on this figure, you can see that the hydride length increases with the load. And we made tests at 50 Newton, and 4 tests on 5 led to fracture. So the hydride grows to a critical length at a given load. To help to understand the experimental observations and to quantify the cracking criteria and the hydride length, we implemented the diffusion and precipitation model in the finite element method code. So it's a fixed law with a hydrostatic stress gradient and a material balance with F, the hydride volumic fraction. So to show you some results, you can see here in the black curve is the hydrostatic stress profile on the ligament here, and you can see the hydrogen concentration in solid solution. So as you can see, this concentration increases where the hydrostatic stress is the greatest. And if we look at the hydride volumic fraction, you can see that it's different from 0, where the hydrogen in solid solution is bigger than the limit of solubility. So our numerical model results reflect the experimental observations, and now we are going to vary the parameters to validate the simulations. So we have seen the first type of DHC, which is the stress-induced diffusion of hydrogen solution and the precipitation. And after that, there is the hydride growth to a critical length, and then there is the hydride fracture and the quark propagation. So now we are going to see this second step. So now we can take a look at the tests realized at 15 Newton. So as I said before, 4 tests on 5 led to fracture. And if you look at the surface fractures, we can see that there are 2 fracture modes. So the green arrow and the blue one. And if you look at the displacement versus time curve for the unfractured test, you can see there is a small increase of displacement that corresponds to creep. And if you compare with a fracture test, you can see that the displacement increases quicker. So it's a progressive cracking that corresponds to the first fracture mode, which is a progressive brittle hydride fracture. And then here you can see a jump that corresponds to a rapid cracking, which is that corresponds to the second fracture mode, which is the ductile Zircaloy fracture. So also, in addition, we saw that we can that DHC cracking can start from a notch and not only from a crack. So, as in the beginning, I said we wanted to determine the cracking criteria. So there are 2 cases. From a notch, so we want to determine the hydride length and the critical stress, and from a crack with the fracture toughness called the threshold stress intensity factor for DHC and quark propagation. So to quantify the fracture toughness, we use a numerical model method called G-theta method. So it consists to calculate G, the cohesive energy, by applying a perturbation eta, and then and we know that this value is equivalent to the Rice integral, which is divided into an elastic and a plastic terms. But our model is only elastic, so we can easily determine the stress intensity factor, and we fit it with the function of the quark length here. So we did that for 2 cases, with the crack and with a notch and a crack. So the correlation is identified for the unnotched case, but is being identified for the notched one. And finally, to model the quark propagation and the quark initiation, we use a cohesive zone model. So this is an addition. This model consists to it's an additionally mesh on the ligament, and it's driven in normal separation. So once the normal separation is bigger than the critical normal separation, there is decohesion and fracture and quark propagation. So this critical normal separation is function of the hydride volumic fraction. So once the hydride volumic fraction is different from 0, the cohesive zone properties are modified. And you can see here a test on the specimen geometry with f equal 1 everywhere, so it's only hydride. And you can see that the cohesive model works on the specimen geometry because the quark propagate. So to conclude, we experimentally show DHC, so the stress-induced hydrogen diffusion at the notch tip and its precipitation into hydride. It's brittle fracture and quark propagation. So now we want to realize tests on pre-cracked specimen by fracture of an hydride at the notch tip to determine the fracture toughness. And numerically speaking, we implemented a diffusion precipitation model and this diffusion precipitation model accounts for the experimental observation, and the stress intensity factor was calculated in function of the crack length. So now we are going to identify the cracking criteria from a notch and a crack and explore different thermomechanical histories. So thank you for your attention.